Hello, everyone. Welcome back. Today, I'm going to be talking about the dot product of vectors. So, what is the dot product? Basically, here's our definition. Given that the vector A and vector B are non-zero vectors and they're arranged from tail to tail, so not tip to tail, but tail to tail, we know that the dot product is going to be the magnitude of A times the magnitude of B times cosine of the angle. So there's three things we have to know or figure out in order to find the dot product. We need to know the magnitude of A, the magnitude of B, and the angle between them. They also can't be, they also must be an acute angle or an obtuse angle, right? They cannot go past a straight angle of 180 degrees, right? So it couldn't be a reflex angle, for example. It needs to be between 0 degrees and 180 degrees for, um, for our theta value. So that's a very key thing as well, just to keep in mind. So, why would we care about the dot product? Well, the dot product has two main uses. We can use the dot product to find the angle between two vectors, right? And so that's one way to do it, right? If we know how to figure out, we know A and B and their magnitudes, but we don't know the angle between them, we can use it to figure that out. So in physics, the dot product is used to find the work done by a force when it moves an object a distance d, right? So work done is equal to the force, the magnitude of the force times the magnitude of the distance times cosine theta, right? The magnitude of the force, cosine theta part of the equation, calculates the amount of force directed in moving the object in that direction d. So those are the ways that we can actually use this, right? This is why we actually care about it. So let's take a look over here at example 1. It says determine the dot product of A dot B given that the magnitude of A is 10 and the magnitude of B is 20, given the 0 angle. Okay, so let's do that one then. So in this case, we would have theta is equal to 0. Okay, so let's figure out our dot product then. So our dot product, A dot B, would be 10 times 20, right? Because I just took those from up here, times cosine of 0. Okay. Well, let's think about that. Well, what's cosine of 0? Well, if we think about our parent function of cosine, the graph, we realize that it's just going to be 1. And so our dot product is 200 in this example. Okay. Now for B, let's do B as an acute angle. And then we'll do right angle and obtuse angle. Now the thing is, they weren't actually very clear, right? They didn't tell us what acute angle or what obtuse angle, so you could put any acute value you want and figure out the dot product for it, and same with obtuse angle. For 0 angle and right angle, it must be 0 and it must be 90 degrees respectively, but for these ones they didn't they didn't specify, so I'm just going to choose whatever I would like. So for this one, I think I will choose an angle of 60 degrees, just because if I choose 60 degrees, I know that cosine of 60 degrees is a half from my special triangles, and so therefore I'll get a nice round number. So if I do this, I'm going to get 10 times 20 times cosine of 60 degrees, and that is equal to 10 times 20 times 0.5, which is going to be equal to 100. There we go. All right. And let's try right angle. So this is where we have 90 degrees. So therefore, A dot B is going to be 10 times 20 times cosine of 90 degrees. Now, what's cosine of 90 degrees? It's 0, right? If we think about, the parent cosine graph, what do we get? We get 0. So therefore, the whole thing's just 0. We can just write 0 there. And then what about an obtuse angle? I'm going to use 120 for this because I would like to, because it'll get us exactly negative zero point 0.5, and that'll make this easy. That will tell us that this is going to be 10 times 20 times negative 0.5, which just gives us to negative 100. So pretty straightforward. So long story short, as long as you use this formula that you're supposed to for the dot product, it's not too bad. It's when we go off formula that we're going to get it wrong. Now let's do another example. Here it says determine the dot product of A dot A. Well, let's think about it. We know that A, that the magnitude of A is 10, right? Although actually this is a separate example. So yeah, no, this is a separate example. Let's say we don't know that it's 10. In this case, they haven't really given us much information, but what we do know about this is that we're going to get the magnitude of A times the magnitude of A times cosine of 0. Now, how do we know it's cosine of 0? Because it's just A dot A, right? So whatever direction the first A is going in, that first vector, the second A is going in that same direction. And so there's not actually going to be any angle between them when we put them tail to tail, right? It's just going to be the same vector twice, pretty much. And so that's why it's going to be cosine of 0. So that means we're going to get the magnitude of A squared times cosine 0, which is 1, which is just going to give us the magnitude of A squared in this case. Good. All right, I want to talk about some other properties of the dot product. So this one actually here, we just discovered now, right? Whereas if we have the same vector twice that where you taking the dot product of, it's going to be the same. It's going to be squared, right? Because cosine of 0 is just 1. But what other dot product properties are there? A dot B is the same as B dot A, which makes sense because we would just switch the order of two things we're multiplying in the equation. So that makes sense why that's a property. Same with number 2, the distributive property. Well, that makes sense as well, that whether we do A dot B plus A dot C, or whether we add B and C first and then have A and dot that, given the definition of the dot product, we're still going to get the same thing. This one we already just proved, so I'm going to skip number 3. Number 4 is very similar, right? We're saying that if we have a scalar k, so keep in mind k does not have this little vector sign on top, so it's a scalar. So they're saying that if we multiply a scalar by the dot product, that's the same thing as multiplying the scalar by one of the vectors and then applying the dot product, or the other vector as well, which same kind of thing. It makes sense that it doesn't matter if we multiply it to one of the vectors before, or if we just multiply it to our result after, it's going to give us the same thing. And then here we can see that in this case, this is similar to number 4 as well, where we just state that if we have k and p both being scalars, we can multiply them through, right? We can multiply them to the vectors first and then take the dot product, or we can take the dot product and then multiply these after. Now, I think it will be easier to, in a lot of cases, just to take the dot product and multiply after, but the goal is to recognize that these are actually the same thing. Good, very good. So next I have another example. It asks if vector A plus 3 vector B and 4 vector A minus B are perpendicular and the magnitude of vector A is equal to 2 times the magnitude of B, determine the angle between A and B. Well, first things first, if we know that they're perpendicular, that means what? That means that they have 90-degree angles. And if we recall, whenever we have a 90-degree angle, what does that mean? That means that the dot product is 0. So what does that tell us about these? It tells us that the dot product, would have to be 0, right? So A plus 3B dot 4A minus B, this would have to be 0, right? Because the dot product of two things that are perpendicular has to be 0, right? That's our rule. We know that. Okay, so let's try and find the dot product because that's going to help us determine that angle if we can figure it out, right? Once we get to a place where we can actually take our dot product, we will get to a point where we know, where we know the value of theta, right? And that's what we're looking for. Okay, and keep in mind here, even though we know that, these vectors here that are combinations, some sort of combination of A's and B's and things like that, even though we know those are perpendicular, that doesn't mean the vectors themselves are perpendicular. That doesn't mean A and B are perpendicular. It means these combinations are perpendicular, right? Okay, so let's take that fact and see what we can do with it. Well, first thing I'm going to do is I'm going to expand my brackets, right? So vector 4a squared, and then outer is going to be minus ab. Then we're going to have 12ab. Looks like we have some like terms already forming. Minus 3b squared, like that. Awesome. Okay, now we can collect like terms. That. Okay, what do we do next? Well, to me, this looks like some sort of a quadratic, right? So our instinct here might be to, try and factor it. However, we just expanded it, right? So factoring it would just get us back to where we started. I think it's about time that maybe we use this fact that the magnitude of A is 2 times the magnitude of B, and we translate this into something a little bit simpler for us. So let's go ahead and let's do that. So let's argue that this is the same thing for times 2b squared plus 11ab minus 3b squared is equal to 0. Like that. Good. All right. Let's continue. What else can we learn from this? Well, we can kind of expand this part here and say, well, this is going to end up being 16b squared minus 3b magnitude b squared plus 11ab is going to be 0. So therefore we have 13 magnitude b squared plus 11 vector a vector b, and that's going to be 0. So that means that 13 magnitude b squared is going to equal negative 11 vector a vector b. Okay? So at this point, I'm actually going to take the dot of a dot b, right? So I'm going to take this product and say, well, we know a dot b is what? Well, a dot b is the same as magnitude a times magnitude b times cosine of theta, right? And theta is what we're trying to find in the end of the day. And then what I can actually do here is I can say, well, we're going to cancel the squared out, one of these b's with this b here, and we end up with 13 magnitude b is equal to negative 11 magnitude a cos theta. Okay, and now what can we do again here? We can say, well, we know that a is just equal to 2b, right? So we can swap that out. We can say 13b is equal to negative 11 times 2 times vector times magnitude of b. And then we can cancel those out and we can just say, well, that means 13 is equal to negative 22 cosine theta, which means cosine theta is equal to negative 13 over 22, which if we punch that in our calculator, we get about 126 degrees when we round to the nearest degree. So therefore, the angle between A and B is going to be 126 degrees. So let's review how we did that. We recognized that some combinations were, were perpendicular, so their dot product would be 0. And we use that information to figure out the angle between A and B themselves specifically by finding, the cosine value when we had our magnitude A and B. So that's how we solve for that one. Let's do another one here. It says if vectors u and v are perpendicular, prove that this is true. Well, the thing is, what do we know already? We already know that vector u plus v dot vector u plus v is equal to u oh, plus u v plus u v plus v squared, right? Or sorry, I jumped the gun a little bit there. So that means we have the magnitude of u squared plus 2uv plus the magnitude of v squared, okay? And then here we have just u squared plus v squared, right? Because here we know that 2 times u times v is equal to 0 since u and v are perpendicular, okay? Right? Because if we have u dot v is 0, right? And then 2 times 0 is just 0, right? And so therefore we proved it, right? It's important to write this fact so it doesn't just look like we're, making the 2 u dot v vanish, but when we actually explain and we show how it's just going to be 0, how, it is actually going to vanish, then that really helps our case. All right, well, that is it for today. Next time, we will be talking about the dot product of algebraic vectors, so we'll see you for that. Bye, everyone.